Yeah, thank you so much for inviting me to speak in a very interesting conference. What I want to talk today is I want to show you how you create literally AI applications. And I want to take you to personal experience of what it is this AI and cognitive science is about. You see, I always say to my students that in the last 40 to 60,000 years, we as human beings, we've been living in this analog universe. I mean, everything we created, our civilization. And in the last century, through a lot of innovation which happened, especially in the last 2 decades, with the provision of things like web technology, we have created what is, or discovered what is called as a digital universe. And if you like, anything that you do in a real life, you can have an analogy of it in the digital universe as well. And then there is also these interactions between the digital universe and real universe, and how we would interact with that through what we call as social machines. I'm not going to go through that, but I'm just trying to put everything in a perspective. So when we talk about artificial intelligence and when we talk about creating this digital universe, data is the building block of this digital universe. That's the reason it is so important. But about a month ago, when I was asked to make the presentation, I was actually going to focus on sort of general concept of cognitive science and how we would build it. But with what has happened with coronavirus, you can see that effectively, if these innovations did not exist, I mean, like 30 years ago, if you had these problems with COVID-19, I mean, the life would be completely stopped. I mean, we're now working through isolation. We are conducting this conference through a platform like Zoom. So you can see that how important it is that you would be able to communicate in this digital universe. And one of the key elements of this digital universe is overcoming the communication barriers. So what I want to talk about is towards the end of this talk, I'm going to show you a little demo of an application which I have recently developed, which is called PixselChat. And this is a video conferencing platform that you can conduct near to real life voice and data communication in 100 languages. And I mean, for example, we are using Zoom now, but the common language of Zoom is English, or is limited to one language. With PixelChat, you can actually communicate in 100 languages, more or less in a live time scale, near live time scale. As a matter of fact, PixelChat was also selected to run on the 5G networks program, which was tested both on 5G but on 4G, Wi-Fi, and it works pretty well. And next week, or in the next week or so, we are trying to release a test version of PixelChat for larger communities. So I want everybody who is participating in this conference to also, if you are interested, I think towards the end, Asal would be helping me with that as well. But without much further ado, I want to actually talk about what is the technologies and what is the innovation which creates platforms like PixelChat. So because of that, I'm going to talk about cognitive science and artificial intelligence, concepts in computational cognitive science. Then I concentrate on 2 areas of applied computational cognitive science, which is vision and speech. And then I show you towards the end, hopefully, a short demo of PixelChat. Cognitive science is actually represented. So the concepts in computational cognitive science is that is to lead a better understanding, comprehension of the AI systems that we are trying to make. And computational cognitive models are models that are using based on cognitive science in order to make these systems work. So when we actually talk about intelligence, so you can see that from the diagram I showed you, you had various different parameters like the languages, would it been study of mind. So, but one of the things is about artificial intelligence. But when we talk about artificial intelligence, before talking about artificial intelligence, we have to understand what is intelligence. And intelligence effectively is the process, according to Wikipedia, is the ability to perceive and infer information, and then would be able to apply it to an adaptive behavior. So as human beings, we actually learn things, or we do a lot of things intuitively. If you were to create these smart machines, these elements and entities that they function within this digital universe, obviously we have to enable them to have these artificial intelligence. And that is what the process of artificial intelligence is about, giving the machine the ability to have intelligence. And by intelligence, we are talking about a machine which can make decisions depending on its predetermined logic and algorithms that we would program. So one thing that it is important is we are talking about intelligent agents, and these are autonomous entities that observe upon our environment, and then they do something to achieve a goal. So a computer can be regarded as an intelligent agent. One thing that you need to concentrate is within the cognitive science, we talk about mostly about salience, and salience is the term which allows objects or effects to stand out from their neighbors. And this is really the way that we are trying to create these cognitive science models and systems. This is really the key parameter, is where the detection of these attentional mechanism plays most significant element in creating the artificial intelligent products. And this is when we are talking about the visual system or auditory systems, there are various different things that we would use based on the salience. I talked briefly about this, but effectively we are looking about stimuli, and these stimuli is what it attracts our attention. So again, coming back to what I said, was that if you are trying to simulate a real environment into a digital universe, we have to do things systematically. We have to stand back and see what is it that it happens, what are the physical processes that happen in the real world, and how we would be able to engineer it into the digital world. So I'm just putting this diagram here. You can see the sort of like a human brain, and then there are various different functionalities of it. For example, the motor, the sensoring, sort of things like the vision. It's about sort of hearing, it's about breathing. So the brain actually has got two functionality. One is to do with what it is like a housekeeping process. I mean, you keep your own membranes, you breathe, and then the other thing is about the functionality of the mind. And the functionality of the mind is all the processes that we do through various different sensations, like seeing, like hearing, like speaking. These are the ones that has been determined with other parts of the brain. So I think most of you have actually have heard about neural networks, but neural networks is really been mimicked from the human brain, which is the way that these sort of like neurons, cell bodies are connected through what is called as axons, which are sending these electrical signals. So potentially, when you want to try to sort of learn or remember something, let's say you listen to a nice music for the first time and you remember it, or you try nice food and you remember it, or you dislike somebody, this is because the pulse that is generated through the brain it goes above certain threshold, and this certain threshold would signal the learning process. And this is really how we would create this type of artificial intelligence and try to mimic it through neural networks. So this is what you can see as a synopsis density over time. So if you see on the left-hand side, you've got these newborn sort of like synopsis is the connection between these various different neurons together. As we grow older, this is sort of like becomes much more populated. And adults have got like 64 billion of these connections within the brain. So as we more learn, it becomes more and more sort of populated, and these connections become more and more sort of integrated. So that is really the idea behind it. So in the case of if you have got an interaction of an artificial intelligence with an environment, is the way that in a simple form we enable a machine to actually do the same sort of stimuli, would be able to attract something and then interact with it by giving the right sort of instruction, which can apply that to do a process. So let's say, for the sake of argument, we need to have these type of artificial intelligence in the entire ecosystem. So for an application like PixelChat, for example, you need to sort of look at the various levels of the process. Would it be from the device? Would it be from the network? Would it be from the cognitive engines? Would it be to the data pipeline? These all have to work in tandem before a system works. And each of these have got its own processing and its own AI embedded functionalities into them before you can have a real functional system available for usage. So when we actually do that, we put all these things together in various different layers. Each of them would be working together in tandem, but they have to also work on a standalone and by themselves. So most of you have seen that there is this pyramid which we call as data, information, knowledge, and intelligence. As I said at the beginning, the building block of the information or digital universe is data. So we create this data, but then in order to make the data, we have to process it into information and then into knowledge. And then the process of data to knowledge is a generic one. So I mean, it doesn't matter what sort of application you are using. You always have to collect the data, you have to clean the data, you have to sort of process it, you have to chuck out the bits that you do not need, and then it goes through a process. So from data to information to knowledge is a generic process. But if you want to make something as intelligence, the intelligence is very contextual. It means that if somebody speaks to you in Swahili, no matter you know what they say, you have to have some sort of a background in the language in order to understand, maybe pick one or two words. So the intelligence is very contextual, and it's very sort of based on the information that you have got, is based on your experience. And this is the process that we've got here, is from bottom to top. Let's say that, for example, we map that on something like a driverless car. So you pick up the data. The data is, in this particular case, is raw data. It's about the information. It gives some sort of like a data stream that it is moving. Then this information gets translated into a more of a sort of like precise interpretation. So the driverless car in this particular case says that this is actually represents the light on, let's say, the junction between Gloucester Road and Brompton Road. And then the knowledge is actually the context that what I'm here talking about is on the left-hand side. It is what the machine or the driverless car interpreted. So the knowledge that the machine extracts from this process is that the traffic light that I'm driving is turned on red. And then it becomes to the intelligence of the machine that it has to apply it and say, okay, if all these processes are happening, it means I have to stop the car. So this is how it gets translated. So from the data to the knowledge, these are all generic interpretation of the machine, but in order for it to apply and have an intelligence, it has to have the right learning and the right concept or background towards it. And again, this is how it maps to the from bottom to the top. So if you come to the human, I mean, as I said, I'm going to concentrate on two aspects of the cognitive science. One is actually when you are looking at the human predictive visual models, is that we do not, as human beings, see a scene and everything. What we see is we see the stimuli created by these objects. I mean, this would be something like a color, flashes, and stuff like that. That our eyes would be concentrating on microseconds or far less than that on certain little fixation points into the scene, and then the brain waves them through as a scene. So initial, so that is how these rapid movements of the eye is actually, which is looking at the certain fixation, it interprets the scene. But we do not, I mean, the eye hasn't got that sort of processing power. It all happens in the brain. And these fixations are things like color, shape, concentration, faces, stuff like that. And these are the fixations, are the maintaining the visual gaze on a single location. So when we actually look through that, these simulations, capacities through these colors and everything get interpreted to what we call as cons and rods, and they get interpreted as a scene. So when we are trying to simulate that using computing, sort of computer vision, it is very difficult. I mean, for us, we would look at something and we would interpret it. But for a machine, we have to literally introduce and teach it every single thing. And it is very difficult for a machine to be able to understand, see something and understand and recognize it in terms of an object. So, sorry, I have talked about sense here. I mean, I come back to this is again goes back to the fact that the object recognition, it's what is the whole idea of computer vision is about. So we would, as human beings, recognize multitude of objects with little effort. But then the challenges of a computer system, it is very difficult, and that's a reason that object detection is very hard. So why is object detection is hard? So you have a look at sort of like detecting objects, would say, within an image through pinpointing its location. But if you are doing object recognition, let's say in the case of this bus, it would maybe be able to detect the object as a bus, but it would not by default recognize if the car has got a front or a back. This has to be taught to the machine. So that's the reason that it is difficult. The other thing is the components of the several components. We would just look at them, we would be able to interpret them, but for a machine, we have to actually teach every single one of these objects with different entity in order for it to be able to recognize them properly. Also, things like the perspectives of an image and its location. This is something that a computer cannot do by itself, and we just do it automatically. But then we have got an object can have different type of, literally indefinite type of forms that we would be recognizing it, but a machine cannot do that. What do I mean by that? For example, if you have got statues, a diagram of statue, you would take this from various different orientation. We would be able to sort of recognize it as the same statue, but a machine cannot do that, because every single time that it looks at an orientation or a different type of presentation of this object, it has to learn this is all associated with the same object. It has to be annotated. and it doesn't know it by heart, it can't recognize it. The other thing which is also very difficult for a computer to detect is things like illumination. I mean, a computer would not be able to recognize this is some sort of a shadowing or illumination. The other thing is the scale, and the scale is completely meaningless for a computer. So one other thing is the occultations, things which cover an object and it cannot detect it. Also deformation. Deformation on an object is again something that computer cannot resolve. Then there's things like inter-class variation. You have got this, for example, you would know these are a type of avant-garde sort of furniture, but a computer would not be able to distinguish, you know, that. You have to actually teach it and give it some sort of a criteria in order for it to understand that. So how do we do object recognitions? Actually, the object recognitions, what we do, we go back into the idea of we create what is called saliency in learning. And we pick up, again, the same way that I discovered a few minutes ago. We pick up certain points within a scene, and then we define that as a point of the sort of fixation. And we let them to start understanding that. But there are two parameters which are significant in computer vision. One is called the edge detection, and the other one is the segmentation. And that is really fundamental in the computer vision. That it is with edge detection is where you get the different different textures changing, or the image brightness changes sharply. And the partitioning is the digital image. It comes from one type of segmentation to another one. And for example, here you would be able to edge detections are formed through various different variety of factors. For example, this normal surface discontinuity, depth discontinuity, surface color discontinuity, and illumination discontinuity. These are all the things that we would, for example, surface normal discontinuity is when you are actually have got, let's say, satellite imaging, and it comes somewhere like in can see the sharp difference between the edge of the cliffs of Dover and the English Channel. So it's the water. It actually detects these as a surface, the normal discontinuity as well as depth discontinuity. So these are how we would be able to teach the machine to understand and look for these the patterns. And then once we actually define that, then we can start looking at segmentation. And by this segmentation, we would be able to sort of teach the machine to look at the certain patterns and then look at these closures within all the data set that you have got. For example, in this case, we are identifying this as maybe a tiger in the jungle, and then we can just take that particular yellow round this thing, and then everywhere that the machine would be able to detect this particular pattern as what we would detect this here or something similar to that. But of course, you know, all the statistics apart. The same is with the feature extraction on the face. And if you look at, for example, things like the facial recognition, is we are identifying several points across the face, and each of them would be sort of like matching to the data set. This is a bit more complicated because obviously what you have to do is you have to identify the object of interest and break it into various fragmented, extracted fragmentation, and then define classes which identify that. So, I mean, I'm not really going to go and tell you everything within computer vision in 10 minutes, but I just want to sort of like give you an idea that if you are trying to sort of, let's say, create an application or a system, we have to really look at its real physical processes in the real world and try to create it and sort of define models and concepts. And then, of course, we have to actually code that. We have to write all the modeling, we have to code it, we have to test it, and we have to do it across the entire data pipeline. So it's a huge task, but somebody has to do it. I mean, if you want to really create new applications and systems, if you really want to exploit the potentials of these artificial intelligence and everything that it does, we have to really work hard for it, and we have to be very, very precise. But the leading light here is our real world, everything that we do in real world, but we have to do it systematically and properly. So this is effectively how I detect and look at the face fragmentations. And but of course, you would be able to then look at various things and apply it to the images and do that. And remember, I mean, the technology of PixelChat, it is not only looking at the images. We're concentrating on the videos. We're concentrating on live videos. So these have to be almost done in literally in a seamless way. And this is one of my favorite Iranian classic musicians. And then what it is important is in order to, if you have got, let's say, an image, it is very important to be able to look at the orientations and also the scale of these things. And that is really why it is so difficult, because a computer doesn't really understand that. It's just sort of like a data in terms of pixels. Now I'm going to move to the second part of this, which is about the speech. And I mean, most of you have heard about natural language processing and natural language understanding. This is what enables a computer to interact with a human being to interact with a computer, and then probably do something like translation, stuff like that. And the speech recognition and natural language processing, these are all the various different elements that we need to have in the natural language processing. So currently you're using sort of things like probably Siri, Alexa, Cortana, and this technology is really looking at the effect has been around for a long time. And let's say in the case of if you have got something like Alexa, what it does is it sort of listens to your voice, it trains it, and effectively generates a back-end sort of like a database. And every time that you speak to this thing, it actually starts to look at the possible answers that it can provide. So sometimes if the device works offline, that's the reason that it makes a lot of mistakes. And even if it is online, and if you have got a cognitive system which is online, then it is also very difficult for the machine to be able to understand anything which hasn't been learned before. But that's the reason, I mean, for some languages, or for some voices, you get a better response than the other ones, because it has worked with it and it trains itself better. So effectively, what happens is that in the case of a natural language processing is you have to define the word, the categories, and then you have to be able to sort of make the structure of the grammar. And then, this is what the translation happens between one language to another, a human to a language. But the most difficult one is if you do machine translation. Machine translation, the idea is something like, for example, Google Translator, that you put something and then it translated it in another language. The way that it works is it actually has to understand the structure of the one particular language and then know the other one, and then be able to sort of like seamlessly translate between the two. So this is how the triangle that it would tell you, for example, if you have got the source language, how you would be able to define it in terms of semantics, syntax, and words, and then translate it to another one. And this is how the machine translations, for example, work. Again, this is a very extensive field. I mean, you have to sort of look at the data structures, how you would relate the data structures, would break them in individual syntax and so on. And I'm not really going to go through that. I'm just trying to sort of give you a bit of an idea. For example, if you have got something like a PixelChat, what sort of technologies actually bump into it and how it should be working. And this is sort of combining two aspects of the cognitive science. One is the speech and the other one is the vision. So if you have got some features, for example, we have got on PixelChat, which we have got a text-to-speech engine, which it actually synthesizes voices as well. And this is also generating another additional dictionary, which is related to the sort of like the phonetics and the pronunciation of individual language. And that is really what it defines the individuality of our voices and our speech. So this is, again, how you would create something like a text-to-speech engine, and this is also have to be interfaced to a technology like PixelChat if you are really trying to generate a text-to-speech engine. So what I'm going to do is I'm going to very briefly show you a video. This is about how the PixelChat works. I mean, currently the version that we have got is much more advanced. This is just to give you an idea how this thing works. So what you see here, there are two people. One is speaking in German, the other one speaks in Chinese. This is the handset of the Chinese guy, and
okay. Can connect.
So what you see here now, again, is that there are two users. One is speaking German, the other one speaks Chinese. This is the handset of the Chinese person.
Well,
and as they speak, it all comes out as Chinese into the speech of the display of the Chinese person, as well as the voice. I mean, there's a synthesized voice to it as well. So effectively, this is a basic version of the PixelChat, which we have now advanced much more, and we are going to put that as a test system using web, so people can go and register at Pixel website, and then would be able to sort of like test that for themselves out of the 100 languages that it is available. So you can sort of like speak in your own language, and the person who would be communicating. So if you like, it's something like Zoom, but the common language is no longer one language, it's the language that you speak.
One question here for you. So from Sarah El Ataif, how did you overcome the visual challenges like scaling and all the ones you mentioned? Do you think there is a way we can teach computers general ways to recognize like our brains do? For example, tell it a car has wheels, etc. Can you see the? Can you read it?
Yes, I can see that. I mean, the fact is that in this particular case, we are not really looking at the object scalability, but there are other applications. For example, if you look at the this particular one, which is the Pixel player, and we are tracking objects and people within the scene. This is very important because you have to analyze each individual frame and each sort of data stream as you go along. I mean, it is a challenging concept, but the point is that what I'm trying to say is that even if you get it work on what level of, let's say, the object tracking, it might still fail if you send it through the data stream and networking and everything. So that is really that's really a problem. So you have to make sure that the entire data stream works well.
Thank you. Any more questions here? 1 second.
I think you can, Asal, if you would send the link for everybody to see the the video. I think it is on the Pixel website. I would really want everyone, if they are interested, to join in and try to see if they would like to test the web version of it, which is going to be available next week.
Yes. Okay. So the link to the website is here. Yes. Pixel.com. And another question is from our previous speaker, Professor Duo Chin. When we choose topic of research, should we choose to let computers work on problems which are difficult for human cognition rather than issues which are relatively easy for us to resolve but very difficult for machines?
Sorry, can you repeat that? I'm just trying to put something in the. Sorry, what? Can you repeat the question again, please?
So, when we choose topic of research, should we choose to let computers work on problems which are difficult for human cognition rather than issues which are relatively easy for us to resolve, but very difficult for machines? So machine learning sort of question. Research.
Well, I mean, it's really, yeah, that's a very good question. I mean, this is actually quite complicated because in order for us to establish if the machine or our algorithms are correct, we have to try to test them on a simple things, and we can't really expect to do. I mean, I think it's very important that we establish this confidence that what we are building the system is really delivering what it wants it to deliver, and that goes back to the models. So I think we have to start from something simple and then expand it further. But of course, we have to come to a point that we should really rely on the technology that we have created to make sure that the answers are going to be correct if we can't, as human beings, test it. I hope, does that make sense?
I think so.
Good.
There's a comment from Duo again. How best to learn machine enhance our knowledge? We need to complement each other rather than substitute each other, which is not very efficient. This is the comment from the previous speaker that was asking a question. Another option is for me to demonstrate the demo from my computer and for you to comment on it. Now that I have.
Okay. Yeah, I think it would be a good idea.
Okay, so I'll share the screen. Thank you. So there's another question popped into Q&A window from S. Peters. I frequently hear universities don't have access to data and resources for AI research and engineering, that Google and Facebook have an advantage. How accurate is this?
I think it is accurate in a sense that because for the first time, this technology is being driven by this domain has been now driven by big technology companies, because they go and sort of like harness or recruit the best graduates, and they start working on doing their developments. But you see, the one thing that it is failing with most of these companies it is really the innovation. And I think in order for these companies, they cannot really focus so much on coming at the cutting edge innovation, because they need to take a lot of things into account. And certainly it is true, because they can pay and they can have the best minds to work for them. But obviously the point is that this is also comes on the realms of research, and I think it comes to a point that the universities, once enough tools are available and the teaching of these subject areas become much more mature, in parallel, in tandem with the technology as progresses, then I think we would be able to see this gap is filling up. And now, I mean, obviously the perfect thing that a graduate can have is to get a job at Google or at Amazon, you know, get a lot of money. But then at the end of the day, they sit down and they work on probably one specific product, which they are not getting connected to the rest of so I think it's the innovation is missing. And if you like it or not, at some stage that is going to be revised and it's going to be readjusted itself.
Thank you. Yeah, so I guess follow-up question would be how your technology is different from Google Chat and Google translating technologies available.
Yeah. I mean, that is actually a question that a lot of people ask because they don't quite understand. You see, PixelChat is a video conferencing platform. And this video conferencing platform means that you speak in one language and the person in the other who speaks another language would hear and receives you in his language. Google Translator is a static dictionary like the one I showed you. And effectively, even the current machine translation concept, it means that you speak to the machine and the machine would translate it into a language and then it comes back either with the audio or with the text. But this is only half the story. PixelChat does the other part. PixelR does the other part because you're actually in the digital world, you're trying to remove the complete communication barriers. It means two sort of, let's say, virtual machines or representation of two human beings which are in this universe, they are actually able to communicate without any barriers. So the Google Translation is a static platform, whereas PixelR or PixelChat is a dynamic platform, and it receives information. It does the translation, and then it communicates it with the second person and vice versa. That is what's the beauty of it. It's not starts half the way. It's not static. It's dynamic.
Yes, that makes a lot of sense. So I wonder why Google wouldn't think this way, the way you and PixelR group thinking.
Yeah, I mean, the thing is that, I mean, I could well claim that the PixelR technology doesn't exist anywhere else. And that I can say that very loud here. The reason is that it's not because sort of likes of Zoom, Skype, Google Hangout, you know, they are not able to do that. But I think the technologies it's been created, it goes back to what actually Mandy mentioned. It's about the information infrastructure. It's about the information architecture, which I think if you look at most of these sort of like advanced, these technology companies, I would say something like 80% of them they created based on sort of like accidental invention. And the whole architecture is based on something simple, which is suddenly got very scalable. So for most of these technologies to be able to really provide some sort of like a innovation, they have to completely redesign their architecture. And that is what, you know, my technology is different because I'm looking from top to bottom rather than each sort of putting every innovation on individual node. That is what the difference is.
Yes, I'm sorry for technical issues, but I think we still got a very good presentation from Sepi. Thank you. And
thank you, Asa.
I wanted to tell everyone to, if you are interested in PixelR Chat, to go to Sepi's website, and there is a contact part, and then you can ask and become part of the testing community for this new technology. Thank you, Sepi. And
thank you.
I also ran